thank you everyone for attending the seminar today. Today we have with us from the broader Giancarlo multiverse, the presence of Bas and John, who kindly offer us the opportunity to take advantage of their visit from the land down under, not Bas, to talk a little bit about ontologies and NLE with us. I will give the floor to you so you can use the time as you know well from your talks back in Praia, Amsterdam, and other talks that you may have had the opportunity to have these days. Please come in. It's we're starting, and I give the floor to you now. Thank you very much for
Thank you. Just before we kick off, just check. I do have two cameras here, in case you haven't noticed, blocking your view. So I will record it just to put on the internet. If anybody's uncomfortable with your voice being heard or something, just raise your hand now so I can keep track of that. Otherwise, we're all set.
Okay, let's start. My name is Bas van der Raadt. I'm obviously not from Australia. I am a practitioner in enterprise architecture, ontology modeling. I work together with Claude and Louise and some of the other people in the group on a project, and that's where we met. And next to my practitioner work, I'm also a founder of a startup, and we're working on a platform to build applications right from an ontology and business rules. So I like to call it an ontology-driven software development tool, and I will show you just, I'm going to give you a very short sneak preview because we're planning a session like this in the near future, and I will talk more about what it is and how it works. So most of the time will be on the thing John Ball will be talking about. And we have, why are we here together? We have this connection. We met actually through LinkedIn. That happens more often nowadays. And I saw what John was working on, and I saw the value right away, and it's really, we both are currently working on something that is, we're trying to use natural language in a way that we feel it should work. So, of course, you all know the large language models by now. It's cool stuff. And it feels very natural. You can interact with the system in your own language, and you get a personal reply back. It's all very cool. But there are also some downsides. Like these systems are not able to do logical reasoning. It's not always transparent how they come up with their answers or how they make their decisions. And of course we all experience now hallucinations are there, and it's not always as accurate as you want it to be. So actually John and I are here to propose an alternative approach to AI. And I know John doesn't like the term AI, I don't either, but let's say what comes close to AI. And it's actually in a two-phased approach, where on the left side there's a person giving an instruction to their AI agent. And before you can process something, you have to understand what the person that gave the instruction meant. So if the system is not able to understand what the instruction is about, how is it going to take the right action? So the first phase is natural language understanding. And only if the instruction is completely clear can you go to the second phase, what we call natural language execution. And I'll be talking about the blue part. John will address the natural language understanding part later. So what is natural language execution? It's a form of AI that delivers directly executable deterministic decision-making systems based on controlled natural language input. So that's where the natural language part comes in. But it's a controlled natural language, so it's not put in anything and it will work. It's in a natural language way specifying the ontology and the business rules that the application should execute. It's a deterministic system, so it's fully predictable what the outcomes will be, and it's directly executable. So there's no code being generated. So as I mentioned, I'm running this startup. It's called Hapsah. What does it stand for? It's a human-aimed platform for semantic app hosting. But it's also in Dutch when you have to do something, a chore, and you want to do it fast, and you succeed. You say Hapsah, you're fucking finished. So sort of this dual meaning. So what does it look like? There's a modeler environment, so you can build your ontology through a graphical interface, but also everything is also in controlled natural language. There's always a textual view and a graphical view. And you can create the ontology, but also business rules. You don't need to use the modeler, you can also use the REST API, and there's also an OWL RDF import, so if you already have an ontology, you can import it if you'd like. And as soon as the ontology is available, it's also there in the runtime. So there's no code generation step, it's always instantly there. So when you add a new concept and give it some attributes, it's right there. There's no compilation or code generation step ever. Of course, the application itself also has a REST API, and every time data is changed, it also creates events that are published for integration with other agents or software components or whatever. So what does that look like in practice? Now I have to do yeah, okay, fine. So you start off with a clean sheet, and you can create all kinds of stuff. In this case, we're creating an agent, a person, and we want to make a very simple application where we're going to keep track of which person is driving which kind of car. So I'm making a person. You have to give in the name, singular, plural, and a definition, because semantics are also important. This is stuff we use in the user interface for the feedback. Okay, so a car is kind of obvious, but if you have more complex domain, you want to give meaning back to the user. We're creating an association, drives, with also a definition, and because of the two-way, you can read an association. You always also have to state the backward verbalization. So it's over there. So if you go back to the modeler, the visual environment, I've got two concepts: a car and a person. And now we have to connect them through the association we just made, the drives one. So this is the controlled natural language part, where you build sentences, but it's controlled, so it's not just type in anything and it will work, but it guides you in how to build the sentences. And now we have in the modeling environment the concepts, the relationship, and always if you hover over the concepts, you can see the definition as well. Now we're adding attributes to the concepts. So a person has a name, it's referred by. Of course, you can add all other kinds of attributes if you want. And the car also gets a name. Of course, you want to give it maybe a license plate number and a color and a type and a make and whatever, but it's to keep it simple. We only give it a name. So now we have everything we want. We've got a car, and a person, the association, and now you can see that the person is referred to by a name. So we're actually good to test the application if at this moment. So you have the button go to app, and the things are instantly there. So you can create a person, give it a name. This call, in case, the very well-known John Doe. And you can create a car. In this case, he's driving a Ford Mustang. My son lost the car, so I had to put it in there. And now we want to connect the John Doe with the car, and yeah, we're done. So it's of course a very trivial, simple application, but I had to keep it within 3 minutes. This demo. So, but of course we can do. Oh, it's looping. So of course you have to imagine if you're in a way more complicated domain, there's way more concepts and associations and whatever. But yeah, it shows the principle. So actually what we are proposing today is a combination of natural language understanding and natural language execution, where we hope to have all the plus parts. So the natural language interaction with the system, but the logical reasoning, the transparency, and the accuracy of a system, like an AI agent. Yeah, you would love it to be. So if I ask an agent to book a ticket for a couple of €1,000, I'd rather have one that does exactly what I said it should do and not mess up. And especially when they have access to the bank account, money's gone, and you have the problem. So this is what I wanted to talk about. It's just a sneak preview. We'll have another session on more detail about natural language execution, but now I want to give the floor to John and talk about natural language understanding.
Thank you, Bas. So my introduction is around next generation AI. The things that I've been working on are brain science. So what is it that our brain actually does? And all of you probably know that the brain's like a computer because that's what everybody keeps telling us. And the problem with that metaphor is that the brain's nothing like a computer, and it basically stops us from progressing with AI. Just the quick story of how I got here. Back in 1984, I was at university, and my professor said we're never going to understand how the brain works. And me, a pretty lazy, 20-something-year-old, thought, well, I've got to prove her wrong. And I've spent the rest of my life trying to prove her wrong. And I'll show you the demonstration of the things that we can do with language that simply follow from the scientific method. So key points. One of the distinctions that I draw between today's AI and the next generation of AI is how we deal with context. So as a human being, you would know the concept of the current conversation. Immediate common ground is the term that my colleague Professor Van Velen uses. So there's the idea that there's this current context, which is this meeting, for example, and then there's background knowledge, which is everything else that we know in life. And so I'll be using those terms throughout this discussion. What's wrong with linguistics? Well, words and parts of speech is too simple. And I just like to use this analogy that Albert Einstein said that a scientific theory has to be simple enough but not simpler. And the idea that language can be modeled just with words or with phrases isn't enough. In terms of things like ontologies, natural science is best, not formal science. For those who don't understand the distinction, natural science is like the Galileo type thing. You're looking at the universe, you see this thing moving through the sky, and then you try and work out, can you see it better? And you start doing observations with telescopes, and you get a better view of what you're actually measuring. And that type of system then allows you to falsify your theory and keep improving. Whereas formal science is a lot harder. So today's large language models, for example, are formal science. I'm going to build my large language model, which is based on these statistics, and I'm going to be able to do everything with statistics. And if it doesn't work yet, don't worry, because I'm just going to keep playing around with my current system, and it can never be falsified because it's just your theory that you're constantly working on. I think robotics is the key to AI. You'll see that in a moment. And in terms of cognitive AI, that seems to be a term that people are using to apply brain science to AI. And I noticed that there was this very famous Sam Altman quote from about 12 months ago. He was saying that AGI, as we've traditionally defined it, will be solved shortly in maybe 2025 or in the next couple of years. And then he follows on by saying in 2025 there's going to be some agents being deployed replacing people's jobs. And, well, it's 2025. There are some agents there. I don't think anybody's hired an agent to actually replace a person yet. And I suspect that's a long way off. So I was looking up that term non sequitur because smarter people than me have used that with me when I say something and it doesn't follow. And so I thought that was a good non sequitur. So definitions, parts of speech. I'm just going to define some things quickly and then we'll get into it. So for those who aren't aware, I suspect in this group, you guys are all over it, but nouns, verbs, adjective, adverbs, parts of speech, that's the system that has been tried since the 1930s. I'm going to use the term predicate and reference, so rather than describing my syntax, I'm going to describe the meaning underlying that. So in terms of predicate and reference, the reason it's important is here we've got a noun phrase followed by a time, an adverb. The party is tomorrow. That sounds like good English. So I can write down my rules and say, here's my grammar. That definitely works. And then I'm going to say the man is tomorrow, and I'm going to say, oh, well, it kind of works, but it doesn't work in that case. So what's wrong? And in this case, we've got a predicate as a noun. In this case, we've got a referent as a noun, and so they work differently. So if we can get the model right, then we'll be better off. And it's a shame Giancarlo's not here because I wrote a paper a few years ago now, which was one of my more popular ones on Medium, and I said that the last ontology we'll ever need is the one that the semanticists have come up with. So the idea that there's very few relations in the world, and we can simply use what I claim the brain does, which is simply following these very basic rules. We're able to then go and implement NLU or natural language understanding. The thing that makes this work in real time. Predicates determine arguments with selectional restrictions. Verbs have arguments, whatever. But if we're using this method, we're able to then work out, if you get parts of phrases, you can then work out, is this a valid phrase or not? And so we're able to very quickly disambiguate possible phrases. The famous, sorry, I'm going to just keep talking a little bit at the beginning here, but the famous Google example, they released Parsing McParseface in 2016, which was the best natural language parser at the time. And what they pointed out was that in English you can get 20 words in a sentence, and that will generate maybe 20,000 parse structures. And if a person is looking at 20,000 parse structures for 20 words, my guess is you're going to be looking for a statistical solution because nobody wants to code all of that up and make it work. But with just that predicates determine arguments model, you can work out if something makes sense in that phrase, and then you can continue. So you can throw out a lot of stuff that doesn't work, like the party is tomorrow versus the man is tomorrow. So an example, destroy and destruction are both are predicates, but that's a noun, that's a verb, and reference are things. And the other part that I found fascinating was that you can disambiguate things like cats is 4 letters. So if I'm saying cats is 4 letters, obviously I'm talking about the letters there. I'm not talking about the meaning of cats. But if you took a traditional grammar, you'd say, well, that's not syntactically valid because cats is plural and you're saying is. That needs to be are, which obviously it's not. And cats are furry, that is grammatically correct. So role and reference grammar, anybody heard of that linguistic theory? Robert Van Velen is the professor behind it. He started developing it in the 80s. And I started my work in the early 2000s to emulate language. And I found that it was a terrible problem because everything I'd been taught, I did years of cognitive science, I'm a computer scientist, but I couldn't make any of the stuff that I was taught work. And I spent 6 months just sitting down trying to get parts of speech and a parser to work. So in 2006, I failed, and I realized after a couple more years of trying that I can bring in things like WordNet as my repository of meanings, but it was still not quite right. And I thought, well, I'm going to spend the rest of my life, the next 30 years, I'm going to work out how language works, because I knew that I couldn't get the meaning of, like, I am happy. There's just something weird about how you can even work out a few words like that. And so to make NLU work was going to be impossible. So then I discovered in a bookshop how role and reference grammar explains the world. And it's got this really complicated diagram. So we've got syntax there, we've got meaning here, and whatever discourse pragmatics means, which I now know is context. It took me about 10 years to find that out. This was good enough. This actually incorporates all the things that as a child that you'd understand. And is this modern? Well, Charles Sanders Peirce, one of my other colleagues, not Peirce, he's one of my other colleagues introduced me to him, and he said, well, back in the 1900s, people talked about words being signs, whether it's spoken or written, and that connects to meaning, and then you use the meaning in order to interpret what's going on. So I thought, well, that's what I'm already using, and that's a pretty good model. Why aren't we using that now? And it came back to this. I think probably the most dominant guy in linguistics is Chomsky for the last 100 years, and the idea of having formal linguistics was a great idea, but didn't work. And the other model that we're working on now is unfairly attributed to Firth, which is just looking at the words themselves. But if we're using that plus this, we can do NLU. I'll show you that predicates and reference being added as the meaning side. So, but before I get into here's a system that actually works, let's just start with here's another system that works, which is a little bit more practical. So if you want to speak a language, how do you learn it? And I did French at school, and I spent 3 years learning pretty much nothing about speaking French, but I could conjugate the verbs if somebody gave me some written French. But to do that in real time, there was just nothing happening. So we've got a company that started, this is our language parent company. We're looking at, for all the people that are learning a language, there's 500 million people that fail to learn the language after they've signed up for the course, and there's lots of ones based on large language models now, and there's lots of traditional ones. So we're aiming for those 500 million learners that actually want to learn the language. And we claim that within 6 months, we can do that with a proven method. And the proven method comes from one of our partners that's been teaching people in China who speak Mandarin how to speak English. And it's worked very well for the last 15 years or so, and we're just going to expand that to other markets. And the thing that Chris Lonsdale, who's our partner in this, he's the guy that's been doing this for a while, he does these weird things. He had a concept of brain soaking, comprehensible input, face phonics, so seeing a face and copying it. And with my brain science, I thought, well, of course, that's exactly how you do it because it makes sense. And he's going, but what do you mean? And I said, well, if what brain soaking is, you put on some headphones and you listen to somebody speaking in the target language. That's it. That's your exercise. Do it for 20 minutes. And guess what? Your brain starts to pick up the sounds of that. And then he'd do a survey at the end and he'd say, did you feel like you were understanding 20% or 50%? And depending on what you answer, you're going to get another bit of brain soaking to listen to the language for more time. But in the brain, we have this auditory cortex here in the temporal lobe, and sorry, that's just the diagram, so I think it's around there. So what your brain's doing is, as it's hearing the language, is it's going to your auditory cortex, and your auditory cortex is just going, oh, that doesn't make any sense, what can I make of it? And it's storing patterns and then taking patterns of patterns. And if you do that for a while without any effort, because this isn't an example of, oh, well, that sounds like this, I think I should, if I see that sound, I'm going to do this and that. No, you just hear it. Face phonics is another one where you're seeing a person speaking the language, and they say something, you say the same thing, you can see yourself saying it, and you can hear yourself saying it, and you're just practicing it. So that's in around the motor cortex area, or Broca's area. You're just doing it. So the technique of learning a human language should apply to the technique of AI. So in terms of the competition, Duolingo, an AI-based system, Babel, Rosetta Stone. So we just did a competitive analysis, and all of the things that require the brain science, we put the ticks in, and the others don't have the ticks. So that must mean that we're going to be a really good company. It's been going for 15 years, and that's so the point is that if we can teach humans language by using brain science, and then we can also apply that in AI, then we're onto something that's of value. Is AI solved? That's a question for the audience. Just get a bit of okay, good. I see people saying no. That's excellent. So this is just going to go through pretty quickly, but I don't believe AI is solved, even though I hear every day in the media that you can't believe the improvement that we're getting. Things that don't work at the moment are just getting better and better, and soon all our jobs are going to be replaced. I think a couple of years ago, 300 million jobs were going to go because AI is so good. But if you walk into a bank now, you know how there's a robot there that says, "Can I help you?" And you say, "I just need to transfer some money." It says, "Oh, where?" And you have that conversation. Yeah, that's when you know that AI is here. It's not here yet. Robotic self-driving cars were promised to replace all cars by 2020 by Elon Musk. Captions, if you seek automatic captions, it's pretty good. It rhymes, not perfect. And in terms of ontologies or storing information outside of Wikipedia, Wikipedia is good because you can just read what somebody's written. But otherwise, there's usually loss in whatever's been written. So my conclusion is that statistical AI is in crisis, and to make it a proper scientific crisis, you need the people that are the experts in the field to start to doubt that they're on the right path. And we're not quite at that point, but I think the general population has had just about enough. But for those who haven't had enough, in Australia, one of the places which I spend a lot of time in, which is why I now have this accent, we're talking to the government about a project that they're looking to run, which is they want to go and build data centers with lots of power coming to them, with water distribution so they can cool these data centers. And we think that's not a good use of billions of dollars of taxpayer money. But they're under a lot of pressure because it's not only Australia, it's all of the Southeast Asian countries are all looking to help support Amazon and Meta and Google that want to build these data centers to run these AI shops. And they want people to build them power generation and water cooling in order for them to do it. And so we're pointing out that's an unsustainable model for the world. There's the IP theft issue where New York Times is suing people, hallucinating, which is the reason you can't use the system if you can't trust it because it's producing errors. The cost, $100 million to build a system, and the bias where it's giving you somebody's opinion based on reinforcement learning or other things. And the lack of progress, this is 1980s concept. Hans Moravec, with other luminaries, that things that are easy for humans, like walking and recognizing faces, are difficult for AI systems. And I think today we can say, yeah, but the Chinese can look at a 80,000 people stadium and say, name every single person who's there. So maybe it's not that hard to do all of those things, but perhaps to pick up a piece of paper or something is still beyond the capability of most machines. If we solve this problem, I'm arguing that we also solve language and a lot of other AI problems. And this is the Hans Moravec problem in action. I'll just show you that again in case you missed it. So we've got a plus sign moving across the screen. And if you want to build a machine that tracks plus signs with machine learning, you can simply move it from one side to the other, and there's one sample, and then you can start the plus sign somewhere else and move it to the same spot or other places. And you can do an infinite number of those, and you've got the plus sign nailed for your training set, and then you can do it with other objects and faces. But the challenge is, and this is the frame problem of AI, there's an awful lot to do to hit your infinity. And I've just done another one that would be hard to deal with. So the frame problem is solved with modern AI. Parallel processing with GPUs basically takes things that couldn't possibly happen in real time and makes them happen in real time by having millions and millions of extra extra processors running in parallel, but it then creates the power issue. The frame problem is described as if you speak to an expert and they have to tell you what their decision-making process is for why they did something, they usually come up with, well, I did this and I did that because that makes sense. But in a logical system, there could be tens of thousands of things that they could have done. And when you say, why didn't you do it? They said, oh, it's not relevant. And for the NLU system that I show you, that's really the biggest problem that has to be solved. Of all of the things that you can do with a bunch of words, how can you do the right things and ignore the rest? And it comes back to context. That's my book. So here's the dog-eaten one. We did this last year because I thought it was important to just get the thoughts together of how did I finish up coming up with this model. We've been working in Silicon Valley since 2013 as well, so between the US and Australia. And it explains how the brain works not as a computer, but based on what we know from neuroscience. And for me, it's the final frontier. It's the final frontier in science because we know everything about everything else, right? If you talk to a microbiologist or a doctor and you say, I've got this thing, what does it mean? They can go to unbelievable depths of knowledge and diagnose it and treat it. In the case of a brain, most people, when I say what's a brain, they'll say it's a type of computer. And yeah, what type of computer? Well, it doesn't really compute like a computer does, but it's a computer. And you think, well, it's not helping us get anywhere because there's a couple of fundamentals that come with the concept of computation you can't get past. For example, with this brain vision model, we've got an eye that connects to these different regions, and the popular model is here in motion. So if you're unlucky enough to get two sides of your brain damage that controls your motion ability for vision, and you see a car coming towards you, you see a car like in still, and then it vanishes, and then you see it again, and then it vanishes. And so you're effectively blind in the real world because your brain can no longer see motion. And you think, well, what is it that puts it in this one part of your brain? And if you say, well, there's a program that runs there and you've lost it, well, yeah, but then how would you learn it? And the same type of thing happens with color, with different, very specific things. And so all of that brain stuff goes in, went into the book to explain how we can deal with that, and it was very helpful for an NLU system. But I like to rely on experts when I'm describing what the problems are. So yeah, I'm good with brains. I'm a good computer scientist, but here's a guy, Tom Dietrich from the west coast of the US. He's like one of the machine learning guys that's been behind everything in machine learning and large language models for the last, since the 70s. And when he was, and this is from a 2022 presentation, he went around all the US universities and he was saying, look, this is what we need to do next. And he got a good reception at most of the big universities, but he's saying that there's statistical models of knowledge bases, not knowledge bases. So the reason a machine's going to hallucinate if it's only got a statistical model of a knowledge base is because it doesn't have an actual knowledge base. And he was saying, put one in, which kind of breaks the model, but put one in. Expensive to update. I like this one, separate linguistic skill from world knowledge. So at the beginning I said, in this conversation in this room, we have this immediate common ground or this episodic memory, but I've got background knowledge as well. And you can share the background knowledge, which is the expense of training up a large language model, because if you go through 1 billion documents and you're processing them all, that's the world knowledge being processed, but you're processing it so that you recognize the language. But you can recognize the language a lot easier than that. And so he talks about episodic memory, world knowledge, and there's details to work out. And hey, I've looked at what people around the world are doing, and in the cognitive sciences, there are people that are really good at all of the things that I've done to kludge together a system, and we can just use that expertise to keep building on the system. And one of the reasons I'm talking to you today is to show you what I've done and see if we can do some things to progress. So there's not that many details to be worked out. Okay, robotics has been revolutionized with the latest things happening in the world. So This is in Beijing 2025, and these are the things about to take over our jobs. This will be the soccer, the soccer team. So they can stand up, that's good. Goal, yes, fantastic, everyone's happy. So world's best soccer players, I'd prefer to play against them than the Brazilian or the English team or the Dutch team. Let's have a look at another type of skill. Right, so here's a dog chasing a ball, and it's never been trained to chase a ball, loves doing it. I've just bounced the ball behind its head, and it's running off across an uneven surface. It's just caught it in its mouth, and it's landed, all its legs are off the ground for a period of time, and the victory lap's about to start. It's a very happy dog. It can do it with a red jumper on, so it's a very versatile dog. And here we're going to go up the hill directly behind it, and you can see the eyes coming around to track it. The legs are moving in incredible ways in order to balance. And this dog has never fallen over. I've done this for hours. It'll just keep doing it, never falls. I've seen it stumble once, but that was sort of the uneven ground. So if we can emulate that for robotics, well, you can imagine what the soccer field is going to look like with this, I don't know, these dogs kicking a ball and running around. Here's the equivalent that also represents state of the art. This is up in Portland from memory. These are machines designed to support industry. Notice that its vision here isn't quite the level of vision that you and I are enjoying in this room. And watch as this egg gets put into this egg cup, and think of how you do it as a person. As you're about to put it into the egg cup, you're using just vision. It's just dropped it. So I don't use vision if I'm putting an egg in an egg cup. I feel it going into the egg cup. I don't break it, and then I release when it's in the right place. And this is my recommendation for not being a robot at home, because it's a little bit bad for your back. So what's happening with our robots? Well, the last thing, for an ontology, there's I think a good example to think through. So we've got a meeting. I want you to build me a database that tracks all of this. 5 people are in a room talking together. There's a room with a fireplace and a view of the Alps. So you should have a picture in your head of that. Now, what sort of code are you going to write in order to describe your 5 friends? Because you know the 5 friends, so you want to bring in everything you know about them, and you want this event to be tracked because it might be important to know what they were wearing and what was happening outside at the time. So the entity association model is not the right one, but that's the one that we're all taught to be using. And so we want to do better, which is where I come back to the semantics is the last ontology we'll ever need, because if you've got your database built right, you simply need some pointers somehow back into the environment. And in terms of context, my argument is that dogs have context, because in order to see that ball, they're recognizing as the ball changes in color and shape, because you're bouncing it and it's moving and it's going through shade. They're tracking it as a single entity, which I think animals have to do. If you're a fish swimming around and you're chasing another fish, you better be sure that it's not a shark and you're a little fish, or the other way around. If you see the shark, maybe you want to swim away. So animals at a very early stage need all of these skills.
John, you've got 30 minutes before questions.
Okay, thank you. So when I'm talking to, because sometimes we do these in libraries to get normal people feedback, not expert feedback. Sorry. In case you thought I was saying you weren't normal. Okay. So I printed this out. This was maybe 12 months ago, 1956 AI Dartmouth. So this is where AI is invented, coined. You've got the people here: John McCarthy, Marvin Minsky, IBM, Bell Labs, and other notable attendees, including Alan Turing, that's fabulous, because Alan Turing's one of my heroes. My first project was called Project Turing. So something just didn't seem right about that. This is the LLM generated content. This is from Wikipedia. Just didn't feel right. Something about it. So I had a look at Wikipedia, And there's Alan Turing. My hero died in 1954, and this was in 1956. So that's an example of a hallucination, and some people are surprised because they've heard that AI is solving everything and is about to take our jobs. But the other thing that strikes me is context with a large language model. So if you're looking for a search engine and you type in something like, "The Wizard of Oz is a good man, what can he do?" Well, we get this answer. He wasn't a real wizard, he's just a man behind the curtain, there's a scarecrow, a tin man, Dorothy. So it's given me all this stuff, which is great, like, that's a fantastic search result. But the problem is, that's not how language works at all. So if I said the Wizard of Oz is a great person, the thing that you'd probably say to me is, "Oh, do you mean from the book or from the movie?" And that's a reasonable question. I'd say, "Oh, it's my neighbor. My neighbor's son calls himself the Wizard of Oz." At that point, all of this stuff is all wrong. So we want to interact with these machines in a very natural way, but it's grabbed Wizard of Oz in context in terms of the statistics, and it's given us the wrong answer, and it's done it in volume. So that's why the background knowledge needs to be separated from the immediate common ground. So let's have a look at the system. This is the one thing we haven't practiced yet, so hey, it's working. Let's just clear this. Okay, so what I'm showing you here is, this is our demo system for corporates. It's showing things that relate to semantics, things that relate to word sequence or grammar, and things that are not really well solved with just a statistical system like error correction. We just go straight to pronoun resolution. This comes from the role and reference grammar example. Beth arrived, she saw Sam, he kissed her. So if we run through these examples, run all. So when we put in those 3 sentences, it comes back and says, because we've just added immediate common ground or context. And now it's asking questions. Who saw Sam? Beth. Who was she kissed by? Sam. So there's passives, there's actives. And it occurred to me that if we can take facts that are put in and then just rip them apart with questions and test all the questions work, well, that's probably a pretty good system for doing all sorts of things in the real world. You'll notice that the speed was pretty quick. I'm sort of going to move quickly here, but perhaps we can get you guys access to this as well after this. But it just runs through all of those things, and it seemed to me all we need to do is find out what would recognize that first sentence correctly. And I'm clicking here on current context. So we got Beth arrived, she saw Sam, he kissed her. We've got these are meaning representations, so which come from role and reference grammar. You know, there's stuff which I think ontologists would be interested in terms of why these definitions are there. If we click on the details here of she saw Sam, we've got she saw Sam, but here we've got Beth saw Sam because we're using the current context, so we know that she has to refer to somebody female and Beth was there. Obviously, you know, to do that in general terms, there's a bit of work, but it's working off a very simple principle there. And so there's absolutely no magic going on. He kissed her. If you ask a question, who was kissed? Well, Sam kissed Beth. So who was kissed? Beth, because the question is resolved in the same way that this is resolved. And if I just go here to the meaning and I type in who was kissed, this is so who is the theme? So effectively, there's some kissing going on. We don't know who's initiating it, but we know the one who was kissed, which is who. So I can take this representation here, I can compare it with my context, and I can pull out the answers. So it's a very dumb system for interacting with language. So if we come back here to other things, so these are the party tricks, you know, error correction. So we launched a company in San Francisco in 2016, and we used this example as the argument. This was obviously before large language models. This is when deep learning's at its peak. So if you say call Beth, no Samantha, no John, no text, not that likely, I guess. But statistically, Siri will call Beth because Siri likes the co-location of words. But here, call Beth, no. Call Samantha, no. Call John, no text. So text John is the answer that we should get. And if we just check the current context here, it says text John. So we're tracking the errors, but we're also able to then disambiguate it. And this is a hard party trick to solve if you're simply using word collocation or word statistics. That's just context demo. So there's just a whole bunch of things that you can see with this. I just like running them at full time because we don't have much time. So who arrived, I don't know. Important thing to answer when you've got no context. Beth arrived, yes, we've added that to context. Who arrived? Beth. John arrived, Who arrived? Beth did and John did. Sorry about the way it generates that. Sue and Dana arrived. Who arrived? Beth did, John did, and Sue and Dana did. So because we're working with code in the background, we can format the generator to do anything we like, including randomization. So when people say language is deterministic or non-deterministic, the non-deterministic one is we say all sorts of things and it's very hard to judge what we mean by that. But in terms of the meaning of it, it is deterministic because does John arrive? Well, I don't know, what was the input there? And so we determine what the answer is. There might be 10 ways we can respond, but it's all covered. So if we look at predicates, one of the challenges I had with parsers was I've got a verb, I've got a noun, but what type? The whole point was just to get the nouns and verbs and get the right sequences. But to work out what it meant, there was another level that we needed. So if you look at prove, these things come from linguistics. So if this predicate here, proving, is that a noun or a verb, is one of the questions you'd ask. But it has these arguments, theorem, professors, and this is probably a better one. You can see here the theorem was proved by the savant, so active and passive, and there's lots of ways of expressing that. There's a meaning that's behind it, which we could look at. What's that one? The theorem's quickly learning proof. So the theorem's quickly being proved by the savant was difficult. So this is a whole sentence of its own embedded in another sentence. And it was difficult. And if we care about, which we do, what this means. So we've got a savant proving a theorem, and it was done quickly. So all of that stuff is part of the last ontology we'll ever have. I can say that because Giancarlo is not in the room, so I would imagine he'd take me to task. But I quite like the approach here, where we're taking language, decomposing it, and then we can then use it in all sorts of ways. One of the things Bas is saying is that if we take the NLU output, his NLE, the execution side of it, can then do lots of things that'll help users on top of just the language. Okay, I'll just show you a couple of things here. This nice little, how many pages have we got? 21. So this is looking at one of the predicate classes. So I said I didn't like just verb because there's lots of different types of verbs. Some of them have lots of arguments and some of them don't have any. But here, so if we've got popping, we have a meaning for it, a meaning representation. All of these forms are generating the same meaning. Okay, so if we're going to pop a balloon, we've only got one argument, the balloon popped, which is being shown in that format. Actually, it should have ingressive at the front because it's a change of state. But I thought, well, I want a system that I can rely on, so I'll build some classes. VerbNet built classes, 250 or maybe 500. I just want to test for all of the things that can change, so positives and negatives, voice, tense aspect. I just want to put them all in and make sure that in a test I get the right answers out. So as I add new words to it, I can run my tests. I can be sure that I'm getting the right answers all the time. So this is a class test. That one's 21 pages. I think the biggest one was like 100 pages. Like if you're paying for something, there's the thing you're paying for and there's the person you're paying, so there's like 4 arguments that are getting involved and a lot of permutations. But we've done it so that we can test an NLU system. It's based on a simple meaning representation or an ontology which is determined by the predicate class itself. And as an engineer, it would be good to, okay, probably don't need my emails. I'm just going to use this little trick here. There we go. Now I can see again. So that's sort of a quick feel for the, what do we call it these days? The
language calculator.
Language calculator. Thank you, Beth. Yeah. I'm the one under pressure. I can't come up with names now. I'll just try and now reconnect that with science, because we've got an engineered solution. In my book, I point out that in 1986 or so, I contacted Marvin Minsky and I said, I've got this great idea based on how I think brains work. What do you think about my idea? And I wrote him some stuff, and he goes, well, there's 2 things you've got to do. You've got to do the science right and explain it to others, which I found out I hadn't done quite right in about 2016. And you need a demo, because there's a lot of good ideas. People think that they're onto something, and then they try and implement it, and then it doesn't work. So you have to do both. I think we're getting to the end of having done both, and it's now time to get more people that know a lot more to poke holes in it. But the scientists of the past have solved all these problems. So here's a guy who I never gave much credence to, Zelig Harris. So 1956, Chomsky's professor, and he said in language it's all about transformations. So not Chomsky's transformations, his transformations. And he was saying if you take a whole sentence like the man is tall, and another sentence like the party is in an hour, and another sentence like the man will go to the party, you can take those simple sentences and combine them into one sentence, and now you've got how children use language. So you get the tall man will go to the party starting in an hour, and now you've got to work it all out, what the pieces are. And so that's effectively the testing methodology I'm proposing. We just take how a predicate class works, we get a linguist to write out our tests, we put the tests into the system and make sure they all pass, which I can say through experience, they never work the first time. You have to find the variations that you've missed. And then the system works for that class, and you just keep doing more classes. And these are the role and reference grammar models. So every sentence of the world's languages, all the crazy languages, follow this model. And if you repackage those sentences into phrases, they all follow this model. There's obviously variations between languages, like the words and the phrases, but you get the gist. And so this was another one of Harris's transformation models. And I'm going to point out there's a significant problem here with the science. So every scientist is worth listening to because they've come up with observations that you should follow. I like this: a tree fell is English, a rock struck a tree, that's English. Here's a whole bunch of nouns and verbs that go together in order to recognize these different sentences. And here's the transformations in practice. Books are interesting. You can transform that into interesting books. Or the bulbs are from Holland. Bulbs from Holland are beautiful, whatever. I guess the bulbs aren't beautiful, it's the flowers later on. So that was the model that was being discussed. And RRG adds meaning and context. So instead of just being stuck with noun, verb, noun, preposition, noun, we can convert this into that's a predicate of its own, that's a predicate, there's its arguments, we can put it together and we can use a standard model. Why do I think RRG is a good one? Well, I did this analysis. So the Roland reference grammar says if you've got a word, it's mapping to some sort of meaning. If it's a predicate, it's got its base meaning. And it then says there's a whole bunch of these standard ways that words can represent meaning. And different languages have different views. So I took the meaning C here, and then I looked at the 100 most popular English words. And one of them is the word see. It's the 11th most popular word, because I guess we're talking about I saw this, I saw that a lot. So there's a representation, XC, XY. So I saw the book is an example of that. But if I don't just see it, if it's like behind something and I sort of see it and then I don't see it and then I see it and I don't see it, it still means I saw it. But in that case, it's ingressive. So I didn't see it, and now I did. Ingressive means there's an instantaneous change of state, now I see it. So there's a word for it in English, spot. I spotted the book. Or glimpse is the one I was thinking of here. This is the semifactive one where you see it and then don't see it. So all the world's languages have these little tricks. I can cause to see, I can show. And then I can do it as an activity, I can watch. I'm intently watching that book. Don't know why, but that's all part of the context.
You've got 10 minutes till question time.
10 minutes, excellent. We're running right on time today, that's unusual. Okay, so on the internet I thought, well, I need to explain this. This is a great idea. This is one of my patents, which it's just part of the system that we built. But in order to recognize this stuff generically, the cat ate the rat continuously, slowly, etc., the system that we're using that's driving this is we basically label these pieces based on what they mean. So because it was hungry, we recognize that whole sentence or that phrase as a potential Y element. Evidently is a type of evidential. And we can work out then as we've got our syntax, we can map it to semantics and we can check whether it makes any sense. If it makes sense, we keep it. If it doesn't make sense, we throw it away and we keep doing our analysis. So that's how the system works. And at a simpler level, you've got examples of predicates here like happy. So happy finishes up in the middle and its argument is she. But depending on how much detail you've got, you can wrap your core argument by where, when, and why. And that's why I say this is a universal thing, because if I hold up a book, my guess is in every language in the world there'll be a word for book, and I'm holding it up. There'll be a different way of saying that, but that model explains it pretty simply. And back in the syntax only days, so in the 1980s, you'd see examples like he was eager to please, and if you want to work out what that sentence is, RRG has two pages in the previous book that says, for all of these things that he calls junctures, here's the interclausal semantic relations for all of them across the world's languages. So if you're eager to please, you take the word he and you carry it forward. He pleases someone. He's eager to please someone. And he was easy to please, that means he was pleased by who? And in the system you can see all of those examples being broken down. I'm just going to skip forward to the. Actually, this was a slide I was putting together just before this meeting, because I thought this is the key point. When you've got the concept of is, or this is a something, in RRG he breaks them into these different types of meanings. So if you say Sally's sister is Bill's daughter, you're saying equals. So this referent here is equal to the same one, and you're talking about one thing. But if you say John is a man, it's a classification. So in order to learn the world's languages, this is the English one, which I know, I'll say this is a something, and I can then use that to make my whole system work. So if I say that's, I'm stealing Beth's example, if I say that's a glub, and you've never heard of glub, I could say, what's a glub? You could say it's a book that is on Chinese Mandarin or something. And then I know that it's a book. And if I know it's a book, I've got my hypernym relation or subtype, supertype. And I can then use that with predicates because I've got a category. And So this is an important one for language learning on the fly. This one is, John is the man I met at the party. It's a specification. You're providing details about this, but you're not defining John, because there's a term for it. Didn't come to me before the meeting, and it's not coming to me now. And then attributive is assigning adjectives, so single elements. Look, I'm thinking that's probably a good place to stop. And Beth,
Sure.
Just passing over to you.
Do you want to flick forward to the... Before we go to questions, I've got a few slides. And would love to hear your questions and comments till up till 2:30. So, how to work with us. I'm Beth Carey, co-founder, as John said. And if you could flick to the next one, John.
I'm trying.
Pressure's on.
Hey.
You'll notice John was talking about the book, and if you want to know more about the themes that he's spoken about today, it's available. Are you clicking forward?
Oh.
It's available up on Amazon in Kindle format, hard copy. We've got a few books here today if you're interested in buying one and getting John to inscribe it before you go home. The next one, John.
I've got my special signing pen today as well.
So how to work with us, between us and universities. There is so much scope for research in this area. Obviously, with all the activity around large language models, it has really shown us the value of that human-machine interface. What we have got and what you've heard summarised to a large degree today is a symbolic approach, a very different approach to large language models. So there is a lot of possibilities for research, taking what we know is the benefit, I guess, of the large language models, but there are problems with it, as Bas pointed out. So you've got the sustainability problem, you've got the accuracy problem, and you've got the transparency / the trustworthiness of it, that controllability that software engineers so need. And certainly in regulated industries or enterprises, they just can't afford to have mistakes, whether it's medical, financial, or legal companies, industries. For master's topics, we were talking about possibilities at Raadt University around that sustainability for enterprise software, the deterministic approach of this invention John has for enterprise software, and the transparency and the accuracy. As I said, though, there are a lot of possibilities, and we have a visiting professor from the Berlin School of Law and Economics, Marcus Scarl.
Hi, Marcus.
He's working in that space between that intersection of large language models and collaborating with us on a symbolic approach to do what the large language models can't do, won't be able to do, and we know that this is potentially perfect for that, what's being called the neurosymbolic union or collaboration between the different approaches. So we'd love to talk to you if you've got inspired or thinking about how you could do more research, because there's a lot to do. As John gives credit to Professor Robert D. Van Valen, the creator of Role and Reference Grammar, there is so much that has been done over decades around that linguistic framework for the world's languages, combined with John's pattern theory, which is the brain science. It is an exciting future if we can actually bring more of the positives for society around that sustainability and accuracy to benefit more equitably society, rather than focusing on some more highly resourced languages rather at the expense of others. As John mentioned, the project, the next John, the project that we're working on as a first minimum viable product is called Speech Genie, and we'll be doing a crowdfunding campaign for that to bring to the world the most friendly, most brain-friendly approach to language learning based on this new science. So you can follow us on at speechgenie.co. And the next, the system that you saw John run through, that is our demonstration system. We've been asked to provide that for research. So as we're starting to do that, as we're talking to universities, that's becoming available now to research and look at the glass box, as Marcus calls it, versus the black box. There's a lot more detail under the covers, as you can see, but it's very transparent. There is so much opportunity there, and as we've still got a long way to build the dictionaries, as we accumulate funding, that will be done, but there's a lot there to play with and understand, play with and explore. So if you're interested in that, I guess we'll talk to Giancarlo about it, facilitated by Claudinaire, on his arrival back. And we've got some links at the end of the presentation in the next slide. So please reach out to us on LinkedIn. And the other links, when you start looking up what the work that John Ball has done, you will find there's a lot of papers. So that leads us now to question time and questions that you might have.
Have a cue already.
Yeah. I found it very interesting how you kind of, in this last part, separated the meanings from the way how you could construct stuff.
Right.
But how would you deal with very subtle variations in meaning? So, for example, I'm looking at the window over there. If I would translate it to Dutch, I would say raam. But the raam also has this association with a frame, which the window perhaps not have. So there are so many subtleties in those meanings. So
yes.
What's your idea of how to deal with that, how to approach these?
Yeah, the good examples are things like very, very simple day-to-day type examples like open. Mm-hmm. So you can have an open personality, you can have an open door, you can cause the door to open, and it's the same type of words being used each time. The observations I've made through simply building a system to do it is that the definitions that we get from a dictionary or from like a WordNet tend to be way too many and too detailed. There's too much context being brought into the definition, and instead of bringing it in to the definition, simply use the context to determine how it's being used. So open is about two things which have a gap between them. It stays open to a certain point, and then when they're touching, it's closed. So those types of things, that simple explanation, I think, in a sentence, then allows you to understand what's going on, but not necessarily get the same sort of dictionary that we have today. So I think there's a big piece of work in that, I've done a couple of simple steps, and we can get the system to work as a conversational agent without necessarily solving all the subtleties of that. But I think there's a big research area sitting on top of it, which is what's the best way of doing this so that we're getting the multilingual capabilities. One of the debates I've had with Robert Van Velen, the RRG guy, is can we do this for the world's languages? And he says no. And I say yes, and we've got a $1 bet on it that we will be able to do it for the world's languages. So that's where I'm at.
When students are looking at the more diverse languages like in South America and Africa, they are recommended to use the Roller Reference Grammar linguistics framework because there is no other that deals with. It was actually informed initially by their research mandate, or was would you create a linguistic framework if it was informed by the most diverse languages in the world? And they included Lakota, their Native American language, Tagalog from the Philippines, Micronesian languages, Australian Aboriginal languages. So they came at it from a very different way to start with. And so he spent his career, and there's hundreds of people, thousands around, students around the world that are looking at analysing the world's languages using that linguistic framework. John presented just in July at their International Linguistic Conference, and he's the only industry representative because computer science has not exploited this to date.
Yeah, because you have to bring it into computer science with the bridge, because Van has a model of the predicate classes, but he's simply representing them as a symbol.
Yeah.
And underneath the symbol, you then have to explain what the differences are. And one of his colleagues from Düsseldorf University is a semanticist, and he's got a whole lot of good things there, but it's just not been fully brought together. I was just holding that book up. There's millions of dictionaries out there. Hey?
It's a glove.
It's a glove, yes. This one's about Mandarin, Chinese, English, but there's 6,000 words that it defines here, and I've got like five or 10 of these books for Japanese and Spanish and so forth. And it seemed to me that if you were to put in the first 6,000 and get them interacting with people, then we're making good progress there. And I've just been holding back actually biting the bullet and doing it without the right size team so that we can get all the tests done and the other things that'll validate it. In Giancarlo's presentation today or yesterday, he has this great example which is on this topic, which was learn to stop worrying about I've got to get it right. So it comes from an old movie about
Peter Sellers.
About the destruction of the earth, and it was learn to stop worrying and love the bomb. So that was about the end of the world through nuclear Armageddon. And there's a guy at Stanford that came out with learn to love large language models with the same concept, and Giancarlo had something like learn to love ontologies, and I thought that the one about loving ontologies is the right path, not. But the reason a guy at Stanford said learn to love large language models was he has exactly that complaint, which is if you take the meaning of a word and you have 10 sentences, and you see how that word, its meaning is being influenced by the other elements of the sentence, you say, oh yeah, that's really hard to decompose. But it's only hard to decompose, I think, until you do the analysis of the dictionary definitions. And then you say, yeah, these two mean the same thing. It's just that in this sentence, the subject and object is influencing it in a particular way.
Yeah.
Yes.
Thank you. Very interesting. I'm not an expert here, but I was thinking of the attempts at the early 2000s that you also refer to, so I know from a colleague at the University of Amsterdam, Rens Spot, you may know him, Professor Rens Spot. He's at the logic department, and he once told that his PhD was on large language processing, where he started indeed from grammar, from using grammar, and so. And he told it didn't work, and then they went over to the statistical approaches. So I was wondering, at that time it didn't work. So what is then new in your approach to expect that it works, right? Because back then it was based on ideas about that grammar indeed helps us in understanding.
Yes.
What is new?
I think the big advantage now is that I tend to draw the world into up to 1990 was all symbolic systems. So the Chomsky version of parsing and the parts of speech, and maybe there'd be definitions. But it was all computer science driven. How do we process these things the right way? Role and reference grammar, Van Velen started in the 80s, and he got lots of good progress done through the 90s and the early 2000s. But at that point, the whole world had flipped, particularly in the US, to statistical techniques. And we're still in the statistical technique focus point. So the advantage that I think we have now is we can look at role and reference grammar, I've got a working system that I can demonstrate, and we can critique it, and then we can see if you really push statistics as from the 1990s to the present. That's been a really intensive period, bringing in neural networks. What's lacking in those neural networks? And I think the things lacking are the accuracy that you get from the symbolic architectures. So I think at the moment in the US, if you're trying to do an AI startup and you're not using a large language model, you probably won't be getting funded. And so it's the same problem the world over. While there's a big hype bubble on a particular technology, it's hard to compete.
In summary,
can I ask a follow-up here? Because I was thinking of Wittgenstein's notion, right, about language games, and that words get their meaning in what he calls language games.
Yes.
Is what you show in that program, could it be compared to a kind of language game of how to figure out the rich meaning of a word?
Yeah, I think so. So I read that in the early days when I was looking at WordNet and trying to tighten up the theory, and that's I think what's really influencing the word vector models at the moment. It's you shall know a word by the company it keeps. Wittgenstein had a slightly different way of saying it, and now that we're taking statistics on such a huge scale, and we're finding that it's got shortcomings around the things that phrases can resolve, the limitations need you to look further. Like we can't just keep increasing the expenditure of processing systems and word vector redesigns and all the other systems that are going into it. Whereas Firth is always blamed for the modern word vector scheme, when you read his the paper that he's quoted from, he's actually saying that in word collocation, so in the case of The Wizard of Oz, those words belong together. It's a pattern of words in a sequence. If I say the Wizard of Oz, you know what I'm saying. It's a book or it's a movie or it's the character. But if I say the Genie of Oz, it's nothing to do with that at all, because now you're converting what I've just said, those words, into their meaning, and the meaning doesn't refer to that literal string. So there's a couple of levels that the people of the past haven't really focused on integrating into their theory. Once you start integrating the word sequence, now you're often getting multiple answers. And as a computer programmer, I don't like that, because now I've got to keep track of two different things and I've got to somehow resolve it. But I think in practice, our brains are doing exactly that. They're keeping multiple patterns in mind, maybe both. I mean, you call something by title because it also refers to the content. So the Wizard of Oz is called that because there is a Wizard of Oz in the story, and so it's both. So that's probably a long-winded response, but
I would summarise from your first question. The difference is, why will it work again when it didn't up until the 90s statistics took over? The new brain science of pattern theory and role and reference grammar. That's the difference.
That was my other answer.
Then I think it was not completely clear to me from the story how the brain science.
Yes, I didn't cover that.
Yeah,
I didn't cover a couple of things.
You focused on RRG, but there's a lot in the brain science of the pattern theory, and you can read more about that. Did you have a?
There was a question. Yeah.
Oh.
Okay. Hey. So thanks for your presentation. I would like to hear your take on the following. It's broader than what you presented. It's a more general question. So we know that our computers use a lot more energy than the brain, right, than the human brain. And we cannot, even AI systems that we have, they consume way more, right? And the brain provides, let's say, services, and they have capabilities that are far superior. And at least for many tasks, at least they are more flexible, definitely. And the question is, what is the secret sauce? Because it seems there is something in the brain, maybe, I don't know if it's software or is it the hardware, because it's biological computation or something that happens in there.
Yeah.
And what is that? Because the gap is huge, you know. You can do things that are very impressive with a lot less energy. So maybe, for example, this thing of scaling up in LLMs in this case, maybe it is actually blocking the progress, because maybe we should scale it down and try to make things more efficient, you know, come up with clever solutions.
Yes.
So
20 watts versus gigawatts is the scale of difference. I didn't cover the brain theory, but the idea is that even for a simple animal like a fish to be able to live in the world, it needs to get vision in, hearing, or other types of touch senses, and it needs to be able to recognize things in each of those sensory areas. It needs to predators and prey. It needs to know the difference. And what pattern theory says is that as each of those senses is operating, it can find patterns in what it detects. So one fish might look like another, and there might be a common pattern there, which is stored in the early cortex. You know, fish don't have cortex, but the idea is that it's storing enough to be able to recognize that when it sees it again. But then at some point, all of those senses have to come together, which is in early brain structures. So the focus of an animal brain is around the sensory experience and the motor control inside of the sensory experience. The focus of a large language model is in the manipulation of language based on statistics, which is a horrendously expensive task to do. Like if you take a large OpenAI system, each word is converted into 3,000 numbers, and then you do statistical analysis between the first word and the second word, where you're comparing these 3,000 numbers with 3,000 other numbers and doing all sorts of statistics. Then you get the next word and you're adding that in. And so the thought that a brain works anything like that is just not very compelling.
The patterns that they, generative AI, look at are very different patterns to the ones that you're talking about, the multisensory ones from the brain.
Right, yeah, it's and an LLM is built to work off a computer because it's built to handle encoded data, not on visual data. Like it doesn't read, it gets the encoded data from the source files. So it's just a completely different system. But I've got some of it in the book, and I've got more in my presentations that I can point you to as well.
Yeah. Okay. I'll perhaps ask an easier question, or maybe two. Okay. So in Project Turing, Project Pat, you mentioned that you started with an example of Sam's kissed pet, and then what you do is that you ask questions, and then you make relationships based on that. Right? You ask a bunch of questions, you add a lot of questions, and then you make relationships with those tuples out of it. Right? And then you also mentioned the predicate classes, the predicate specification classes.
Yeah.
Like where you mentioned balloon pot, and there's a lot of ways of saying that same information, saying that same thing.
Yes.
So first question, do we make all of these questions, all of these cases ourselves? Like someone sits down like you or some guy, and then you make all of those classes yourself manually?
So the language defines how the predicate classes work. And so somebody who's a linguist can say, for Spanish, this is how I would build a sentence, and here's then the variations. And by having the native speakers do that work that are also linguists, they can then get them right, and then you can test it. And ultimately, as a computer scientist, I just want to keep running more and more tests against the classes, because if the tests work in scale, then my system's going to work generally.
Okay. So if we were to take that, let's say I want to deploy a real world system, let's take an example of financial contracts or legal contracts where the conditions are very, very set specifically, like we know it. So maybe it's a little stupid example, but will we take any statement, like one statement from that contract, and then based on the language, we will ask a bunch of questions so that it understands or gets the relationships between different entities in the contract.
Yeah, I think I get what you're saying. So if you've got a contract, what you'd want to do is read all of that into context.
Yeah.
And then when a question comes in, you want to be able to ensure that out of all of that context, you give the right answer. And sometimes you're going to need to clarify the question because it'll be ambiguous and you'll get some multiple answers, so you might have to give multiple responses. But for me, if we can build a system where you put in a lot of context, you ask questions and you get the right answers, you're understanding what's going on there. And then again, it's a test that proves that your system's working correctly. Because as a computer scientist, the more tests we do against more data that give the right answers, the more reliable, when you make other changes to the system, you rerun all your tests, the more reliable you can say the system is because all my tests have passed, so now it's ready to go out. Yeah. So the big question under it is if I give you 10 million facts and then I ask a question, how can you efficiently do that? And that's where the pattern theory concept comes in, that the question has its own context, and if you intersect or you take the common pieces with all of your context, because you're not allowed to duplicate elements in the system, the question determines what's valid to look at, and you don't have to look at anything else. So that's the frame problem being resolved. That rather than search, I've seen some great search detail on the walls up here in the faculty, and I thought, well, that's great, but we're trying to get away from using search for the brain emulation. Yes.
So while your current implementation seems to use the immediate common ground, does it also update the, what was the other one?
General common ground.
Yeah.
It doesn't. So the more we talk, particularly at universities, the specialists at Sydney University said, how do you deal with background knowledge and how do you bring it into immediate common ground? And, oh, yeah, I haven't thought of that. So that's why I'm talking about it. The principle would be, though, that you would want documents or books brought into the system, make sure that you've got the right content so that you can use it. And when that project is run, that's the time to improve it. So at the moment, no, we don't do that.
I also have a question, so it's basically to both presenters. So you have shown these examples, like small controlled examples, where you feed your system with a set of sentences. Now, I have a following experimental setup. I feed the same set of sentences to your system and to an LLM, and I'm then asking some questions to both systems. And both of them should be able to get the context, the LLM because of the length, the token length, and the your system because it simply stored the facts. Would you think there's certain measurable advantages of your system, despite it being fed with very little knowledge that could be directly measured in such a comparison as compared to the LLM?
Will I answer first? Yeah. So from my perspective, if you've got input facts and you've covered the vocabulary of all of that, and we've correctly stored them in the right predicate classes, then you're able to identify what's being meant by the question and how that relates to your potential answers, your facts.
I would have the experimental setup in a way that I would have the same things given to both systems, and then I would have a certain set of questions or a certain set of, let's say like a certain set of questions, and I would analyze the answer, and probably the LLM answers would be more talkative, maybe better expressed, nicer communicated, etc. But what would be the advantages you would expect in your system in the quality of the answers that could still be measurable, even though probably not seen on the first sight, because it looks like more simplistic answer type?
So the biggest advantage of a system that's not an LLM is saying I don't know. So if you don't recognize something because it's not a fact, you can say I don't know, whereas an LLM's forced to give the most probable response by its design. So I think there'd be a bunch of things that would be testable and different if you did the work.
Robustness, I would say.
Sorry?
Robustness, so there's less hallucination, I think, in your
No,
approach.
no hallucination, robustness,
Repeatability, maybe.
repeatability,
Yeah.
low turnover.
Energy that you talked about.
Right.
Energy, right.
Energy.
Half a liter of water or versus...
Say it's a half litre of water.
Yeah, we have a benchmark. I don't think I mentioned it in the talk, but Facebook ran a bunch of they ran a bunch of conversational tasks in 2015, 2016 under when Jan LeCun joined, and their idea was they were just going to keep iterating and improving the conversational tasks. But then they pivoted to doing what everyone else was doing for some reason at Facebook. But we took on those tasks in 2017 and we got 100% on all of them. So that's an example of what you could do. But the other thing that we did was we didn't like some of the incorrect answers we got from the Facebook data set. And so we then tested their training data and we found errors in the training data that causes errors in the output. And so there's things that you can do with this technique that you can't do with the machine learning system.
Yeah, I was also thinking about control, basically what you're also saying, right? You can control it better. You said it's perhaps better phrased with the LLM. I like very concise answers, right? And I cannot control the LLM to give me... Yeah, but this stuff you could control much better.
And I think one difference is maybe also the LLMs are trained on data where there's a cut-off moment. So if you have a system that had new knowledge put in just from a week ago, an LLM doesn't know. I mean, it has a certain date where it says I stopped knowing.
Okay, but I would of course I would prompt the LLM say that it can only respond from what it just got, like from that context. So I would not, of course it could still do it, but I'm trying to get at a particular point in quality of conversation, and not so much on the more ontological question of whether what is coming out is correct. I'm not, because this is by the way a very different aspect of it, yeah, because if you feed bullshit in, you get bullshit out, that's always the case. So I'm not exactly interested in this aspect of it. So I think it's really interesting. So what would be your answer to my question?
Well, the same. I mean, for what we're building, there's no conversation engine in there, so it's just a factual system.
Okay.
And it will just say, if you ask them a question, so query for facts, it doesn't know, it will say, I don't know. So
okay,
it's always an honest answer. Plus, you can always, what we try to do is keep track of where the information came from. So if you ask an LLM, like, you gave this answer, can you give me the sources? It oftentimes cannot, because it's not explicitly available. So it's really about being accurate, transparent, and also the stuff we're building, it can run on a single PC without a problem.
Yeah.
Where you don't need this gigantic data center for it to work. So I think those are the obvious differences.
So I have one follow-up here, because basically your slide from the beginning was inspiring me for that question, because you said, okay, we have here this green text, tick, 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 and now, wow, there's some red crosses, and now we want to make them green ticks as well. But I'm still wondering, how do I get it across? You know, like LLMs have the vocabulary still, and it seems rather tedious to get all of these expert knowledge linguistically into your tests. So that's why that's my main concern actually.
Yeah, but I mean, I think John is also addressing it in his talk. I mean, there has been a gigantic investment in these large language models and the preceding technology.
And we just want a little bit of what they've had. But yeah, I know you know, and any bootstrapping that can be done because of your wonderful research around what LLMs can do, it is finite, I guess, and it gets back to your point, perhaps your question, it's more finite. There is about 250 such classes in, as RRG would say, and whether it's 300 or 150, it's quite finite. There's always new words, so like a glub, you want that learning to happen on the fly, like it does with a human. But there's a core that we're working towards. We've got some dictionary in there, we've got some languages represented, but yeah, there's a lot more to do.
Yeah.
As a context, I'm proposing basically to use, let's say, a neutral large language model to have a specialized agent to support that creation of knowledge that is needed to lift up such a system, just for the context of what you're saying.
And one of the things that I look at is when we build this system out, let's say it costs a quarter of the cost of one training run for a large language model. Once you built it, the language doesn't change very much. So potentially you can build this thing once, use it for all sorts of applications because it's converting text or sound into meaning, and then you're building off the meaning side of it. You don't need to keep investing in another training run because once you've got your dictionary, it's
a
done.
build once.
It's a build once and maybe run for 20.
The same is true for LLMs. You don't need to keep investing more. You have trained the models. I mean,
I think they keep rebuilding them though to improve.
Right, but why? Yeah.
Right.
To get to eke
and you're
out
the expert there, so.
to keep eking out a bit more improvement, and that's questionable whether they can.
to rerun it completely with a new angle or whatever. That's true.
I think that maybe I will have my own questions, but maybe I follow that from.
Yeah, sure.
Oh, sorry.
Thanks.
Bye-bye. Thank you very much for attending. Thank you again, Bas and John and Beth, for the very instigating presentation. I will ask you to share the information for the audience on how to follow up with you, because we already have a direct contact with you for collaboration and so on. But I would like also to forward that information to the audience as well. Maybe the slides from today, because they are a little bit different from the ones we have from the QR code.
Yes.
I don't know which version would be best. To share.
We'll do the latest.
Good point. Yeah, we'll talk to you about that then.
Okay, perfect. Thank you very much again, and thank you everyone for joining.
Yeah, thank you very much for having us. Thanks.